Okay. Today is a review section for the final exam. Okay. Final exam. The time is the day is May 12th. It is a Thursday, and the time is 11:15 a.m. to 12:15 p.m. 2 hours. 2 hours. The location is classroom building 118. This room is different from the room that we use in exam 1 and exam 2. Okay, pay attention. This is a new room. Okay. The final exam is comprehensive. It covers section 1.1 to 1.5, 1.7, 2.1, 2.3 to 2.3, 2.8, 2.9, and 3.1 to 3.3, and 5.1 to 5.3. In total, 17 sections. 17 sections. The percentage, about 20% of the problems in the final exam from these 5 sections. These 5 sections were covered in exam 1. And about 30% from these 4 sections. These 4 sections were covered by exam 2. And 50% from these sections. These sections, I taught these sections after exam 2. After exam 2. The final exam is closed to the book and also to the notes. But you can have 2 this time, not just 1, 2 formula sheets to the final exam. The size is A4 size, A4 size. And of course, a basic calculator. About the formula sheets, you can write anything you want on the both sides of each formula sheet. Okay, yeah. How to prepare for the final exam? Of course, review your homework assignments and review your exam 1 and exam 2. The solutions to the homework assignments and exam 1 and exam 2, you can find them on wild courses. Second, I suggest read some examples in the book. Okay. And if you still have time, try some problems in the exercise sections in the book. Okay, now today, let's have a review about these sections. For the sections covered in exam 1 and exam 2, you can take a look at the videos that I post on YouTube. Okay, about these sections. Take a look at the videos post on YouTube. Now, today, I only focus on these sections. Okay, yeah, let's take a review section by section. Refresh your memory. Section 2.8. Section 2.8 and 2.9 together. Okay. 2.8 is about subspaces in RN. Okay, subspaces in RN. What is a subspace? Write down the definition on your formula sheet. Okay, definition. Yeah, definition. Let H be a set in Rn. H be a set of points or vectors in Rn. If H satisfies the following three conditions, then we say that H is a subspace. The first one is the origin of Rn should be in H. Yeah, H should contain the origin. Okay. B, H should be closed under scalar multiplication. For each vector from H, it is closed under vector addition. For H, for V from H, U from H, then U plus V should be still in H. This property is called H is closed under vector addition. Now C, H is closed under scalar multiplication. Yeah, for each vector V from H and each scalar, say C, okay, then C times V should be in H. This is the definition of a subspace. Say for example, actually this is a homework problem. Yeah. In R2, suppose we have a set of vectors in R2. Which set? Yeah, this set. Say for example, this set. Yeah, all the points in the first quadrant. Okay, quadrant. Yeah, this set H. This H is not a subspace. H is not a subspace of R2. Why? Why H is not a subspace of R2? Go back to the definition and have a check these three properties. If one property is not satisfied, then H is not a subspace. You know, 0 is in H. Yes, 0 is in H. 0 is in H. Property 2. For any two vectors in H, their sum still in H. Yeah, arbitrarily pick two vectors. Pick one. Pick two vectors. Now their sum by parallelogram, their sum is the diagonal of the parallelogram. Yes, the diagonal still in H. So satisfy property B. How about property C? I don't think H, this H, satisfy the third property. Because if I pick a C, the scalar to be -1, for example, and pick a vector, say this vector, this green vector from H, yeah, this green vector from H. Then let me call this vector, vector V. Then negative C times V, it is a negative V. Negative V is outside H. So this set has no property C. Therefore, H is not a subspace of R2. This example is a homework problem. Take a review about your homework assignments. Okay. Subspace in Rn. The second important concept from these two sections is a basis of a subspace. Any subspace has a basis, not just one basis, has infinite many bases. Then what is a basis? Definition, okay, definition. What is a basis? A basis for a subspace H. H, of course, it is a subspace of Rn. A basis is linearly independent. Linearly independent set. A basis is a set of some vectors in H. Those vectors are linearly independent. That means that you cannot drop any of vectors in the basis. Okay. It's linearly independent set that span H. A basis, the vectors in a basis span H, and none of them cannot be dropped. That is called a basis. In other words, a basis is a smallest spanning set of H. This is A. B, dimension of a subspace is equal to the number of vectors in a basis. The number of vectors in a basis is called the dimension of the subspace. Any example? Take a look at some examples. Say example. Say example. Problem number 13. Section 2.8. Let me pick this problem to present. Okay. Determine if the set of these three vectors together, they form a set. Determine if the set a basis for R3. That means that determine whether these three vectors span R3, and also these three vectors are linearly independent. Okay. The main point is, so these three vectors are linearly independent. If linearly independent, then because R3 is a three-dimensional space, each basis has three vectors. So if these three vectors are linearly independent, they form a basis. Okay. How to show they are linearly independent? What it means, linearly independent. Solve this equation. Solve this equation. Okay. Is 0. That is the definition of a linearly independent set. Solve this equation. If this equation has only zero solution, then these three vectors are linearly independent because R3 is three-dimensional. So these three vectors can span R3. Okay, yeah. Solve this equation for x1, x2, x3. If the solution is zero, then linearly independent, and therefore these three vectors can span R3. Okay, yeah. So solve. Actually, this is a linear system. This is example 1. How about example 2? Say, this is a problem. Number 20 in section 2.8. Again, same question. Determine if the set 1, -6, -7 a set of 4 vectors. Determine if the set is a basis for R3. Now this time, the answer clearly is not, because R3 three-dimensional. Each basis has only 3 linearly independent vectors. Now this set has 4 vectors. This set is not a basis. One of the 4 vectors linearly depends on the other 3. We can drop 1. Okay, so this set may be a spanning set of R3, but not a smallest spanning set. This is not a basis. 4 vectors, not a basis. Okay. 20. No, 20. Okay. Subspaces. This is an important concept from these 2 sections. The second important concept is basis of a subspace. Now the third one. Number 3, from section 2.8 and 2.9. Column space of a matrix and no space of a matrix. What they mean? Definition. Okay, definition. Now, matrix A be an M by N matrix, not necessary to be a square matrix. Okay, M by N, general. How about let me cut the matrix A into columns. First column A1, second column A2, and AN, N columns. Okay, then column space of the matrix. Definition is the set spanned by the columns. The set spanned by the columns. This is the definition of column space. How about no space? no space. Write down the definition on your formula sheet. No space is the set of solutions, all the solutions of this homogeneous linear system. Yeah. So to determine no space, you need to solve this linear system. Okay. This linear system. Yeah. This is the concepts of column space and row space. Now, two theorems. Okay, two theorems. Theorem number one. Theorem number one. Okay. A column space. It is spanned by the columns of matrix A. This spanning set may be not a smallest spanning set. We can drop some of the vectors, but still span the same space. Then, which vectors we should drop? Which vectors we should keep? Based on the following theorem. Okay. The pivot columns. Yeah. Determine which columns are pivot column. How to see which columns are pivot columns. Reduce the matrix A to epsilon form. Then you can see pivot columns. The pivot columns of matrix A form a basis for the column space. Yeah. So draw 3 columns from this spanning set. Keep pivot columns. Then we have a smallest spanning set. Okay, a basis. Theorem number 1. Now, theorem number 2. Theorem number 2. For any matrix A, matrix A, the size is n by n. Okay. Number 1, dimension of column space is equal to dimension is the number of vectors in the basis. Dimension of a column space is equal to the number of pivot columns of matrix A. How about the dimension of row space? Dimension of row space. It is equals to the number of free columns of matrix A. Yeah, 2 important theorems about column space and row space. Okay, let me show you example. Section 2.9, problem number 13. Okay, problem number 13. Okay, problem number 13. Problem number 2.9. Problem number 13. Yeah, here. This is a problem number 13, section 2.9. Find a basis for the subspace. For the subspace spanned by the following 4 vectors. Vector V1 is 1, 3, -3, 2, -4. Second vector, -3, 9, -6, 12, vector 3. This is a -1, 4, 2, and then vector 4. Yeah, these 4 vectors together span a set. Okay. Yeah, let me denote the set by H. These 4 vectors span H. The question is, can we drop some of them? The remaining vectors still span the same H? Find a basis. How to solve this problem? I suggest use theorem number 1. Okay, theorem number 1. H is space. Now, the solution is solution. I first form matrix A. Put V1 as first column, V2 second column, V3 third column, V4 fourth column. Then H actually is equal to the column space of matrix A. Okay, now I can use theorem 1. Okay, column space. Now each V vector is a column of A. Now I determine which column is a pivot column and only keep pivot column to get a basis. Okay. Okay. Now A, matrix A in detail is 1, -3, V1, and -3, 9, -6, 12, 2. Yeah. I want to see which column is a pivot column. So I reduce the matrix A to epsilon form. Then I get 1, -3, 2, -4, 0, 0, 5, 7, 0, 0, 0, 5, 0, 0, 0, 0. Okay, now I can tell first column is a pivot column because in the epsilon form, first column contains a pivot. Second column is a free column. Third column contains a pivot. So third column is a pivot column. And the fourth column also contains a pivot. So the fourth column is a pivot column. So 4 vectors, pivot column V1, V3, pivot column, V4, pivot column. I can drop V2. V2 is a free column. V2 can be written as a linear combination of V1, V3, and V4. In other words, V2 can be spanned by V1, V3, V4. So here, okay, I can drop V2 from the spanning list to get a smaller spanning set. These 3 vectors form a basis of the subspace H. Yeah, use theorem number 1 to solve this problem. That, yeah, that. Any other example? Let me see. No, this is only one example that I choose. Now, turn to take a review about section 3.1. Yeah, 3.1. Review 3.1, number 2. Section 3.1. What? Section 3.1 is about determinants. Okay, determinants. Okay. There are some formulas to compute a determinant. Write down those formulas on your formula sheet. Okay. To compute a determinant, formulas. A, you can expand the determinant across any row. Say the ith row, any row, the ith row. Okay. The formula is this. Okay. The ith row determinant is equal to the ith row of matrix A. Here A, I assume a square matrix. For a rectangular matrix, we don't have determinant. Okay, this is a say n by n square matrix. The formula expand determinant across the ith row. The ith row first entry is I1. No, my son is here.
Can you call mom, please?
No, I'm having a class. No, go away.
Mom, please.
Across the first row, the entry, first row, the first entry is AI1, AI2, AIN, okay, first row. So AI1 times CI1 plus AI2 times CI2, AIN, CIN. That is the formula. One is C. C is called cofactor. The formula for IJ cofactor is -1. The power is I plus J. -1 to I plus J. Then times determinant of capital A, IJ. Capital AIJ is the matrix obtained by delete the ith row and delete column J of matrix A. Okay, yeah. Write down these formulas. Yeah. Write down these formulas and these formulas on your formula sheet. Okay. Yeah. Second formula. You can expand a determinant down any column. Say the jth column. The jth column of matrix A is A1J, A2J, and ANJ. The jth column. So the formula is A determinant is equal to A1J, C1J plus A2J, C2J, and ANJ, CNJ. Yeah. Write down this formula on your formula sheet. Okay. Yeah. This is section 3.1. Now section 3.2. Number 3. Section 3.2. What 3.2 is about? 3.2 is about compute a determinant by reducing the matrix A to epsilon form. Okay, yeah. This is a determinant. Determinants and row operations or row reduction. Okay, operations. Yeah. To refresh your memory, take a look at one example. Say this is a problem number 9 in section 3.2. Okay, 3.2, section 3.2. Problem number 9. Yeah. Compute the following determinant by reducing it to an epsilon form. Compute this determinant. Zero, 5, 3, 3, -3, -2, 3. Compute this determinant. Yeah. According to this problem, don't use the formula here. The formulas here. Don't use this. These formulas, we call them expansion cofactor expansion formula. We don't use cofactor, but use row operations. Yeah. Okay. First, I use number 1 to eliminate -1. The operation is row 1 plus row 3. Then put the result in row 3. This operation doesn't change the value of the determinant. Yeah. Okay. Row 1 add to row 3. This operation doesn't change the value of a determinant. -3 add to 5, 2, 0 add to 3. Yeah. Then I use this pivot number to eliminate this number 3. -3 times row 1, then add to row 4. Put the result in row 4. Again, similarly, this operation doesn't change the value of the determinant. So here I use an equal sign. Okay, they are equal. Okay. -3 times row 1, add to row 3. -3 times this, add here 0. -3 positive 9. So 7. Then 3. Yeah. Okay, then continue to reduce the determinant to epsilon form. Now this time I use this number as a pivot number to eliminate -3. The operation is row 2 plus row 3. Put the result in row 3. This operation doesn't change the value. Okay. Yeah, just refresh your memory. Okay, now row 2 add to row 3. Row 2 add to row 3, 7. A determinant is a number. So this number is equal to this number. Okay. Yeah. Let me erase and continue my solution here. Yeah. Continue my solution here. Yeah. Here. Okay. Now equal. This time I use this 7 as my pivot number to eliminate this 7. Now the operation is -1 times row 3. -1 times row 3. Add to row 4. Then put the result in row 4. This operation doesn't change the value of determinant. This is a +1, -1, 3, 0, 0, 1, 5, 4, 7, 7. Now, yeah, so 0, 0. Yeah, 0, 0. Yeah. Okay, now we have the determinant now is a upper triangular form. An upper triangular determinant, its value is easy to get. The value is just the product of the main diagonal entries. So it is a 1 times 1 times 7 times 0. So 0. So determinant, the value is 0. That means, in other words, the matrix is a singular matrix. The matrix has no inverse. Yeah, just refresh your memory. Here, I didn't use interchange two rows. When you interchange two rows, remember, add a minus sign. Okay, add a minus sign. And also in this example, I didn't factor out a vector in a row. So actually, you can take in this row, 7 is common. You can take 7 out. But here, I didn't use that row operation. Okay. Yeah. This is section 3.2. Oh, one more example about section 3.2. Yeah. This is a problem number 46. Section 3.2. Let matrix A and B be 4 by 4 matrix with determinant of A 4, determinant of B -5. Now compare the following determinants. A, determinant A times B. We have two properties that we often use about determinant. The first one is A times B determinant is equal to A determinant times B determinant. We often use. The second property that we often use is A transpose, then determinant is equal to determinant of A. So take determinant, take transpose. Taking transpose doesn't change the value of a determinant. All right, now I use this property to get this equation. Determinant of A times B is equal to A determinant times B determinant. A determinant number 4 given here. B determinant -5. So the answer is -20. B determinant of 3 times A. What is that? We have a formula. For n by n matrix, a number times a matrix, then take determinant. It is equals to C. The size is n by n. So C to n times determinant of A. Yeah. All right, now I use this formula. Now 3 times A, 3 times all the rows of A. By formula, it is a 3 to what is the size of A? 4 by 4. So C 3 to 4 times determinant of A. It is a 3, 4 times determinant of A is 4. Yeah. So this is the answer. Yeah. Part C. Find determinant of B to the 4th. B to the 4th. That means that B times B times B times B. Okay. By this formula, we have a determinant of B times determinant of B. So it is a -5 times -5 times -5 times -5. So calculator to get determinant of B to the 4th. D. Find determinant of B times A times B transpose. Again. Yeah. B transpose determinant is equal to determinant of B. So we get -5, B determinant -5 times A 4, then times -5. Then calculator. Yeah. C, A, B, C, D, E. Yeah. How about this? Determinant A times B times A inverse. By this property, then it is this. Okay. Yeah, it is this. Okay. Now, determinant is a number. A number times a number times a number. I can write it as this number times this number, then times B. Yeah. Okay. Now, this determinant times this determinant, use this formula again. It is A times A inverse determinant. Yeah. A times A inverse is identity matrix. Identity matrix determinant is 1. So it is a 1 times determinant of B, -5. So the answer -5. Yeah. Yeah. Done. Okay. This is a good problem. This problem we need to use, some properties. Okay. Yeah. Take a review. The next section is section 3.3. Applications of determinants. There are 2 applications. The first one is Cramer's rule. Yeah, Cramer's rule. The formula is it is a field. Yeah. Okay. To solve this linear system, yeah, we can use determinant to solve the linear system. Because our determinant is only for square matrix. This is a square matrix, n by n. Yeah. To solve this linear system, you can use determinant. The formula is here. Okay. Xi, the ith entry of the solution. Solution is a vector. Okay. The ith entry, okay, is given by this formula. Determinant A, I, B over determinant of A. What is AIB? Where? AIB is the matrix obtained from the matrix A. Matrix A is A1, A2. The ith column is AI and AN. Right? Then, yeah, this is matrix A. AIB replace column I by the right side B. Yeah, this new matrix is AIB. Yeah, compare determinant of this new matrix, then divided by the determinant of A. You get the ith entry of the solution. This is one application. A second application is we can use determinants to compute inverse. Okay, yeah, inverse. Compute inverse. The formula is okay. Form the matrix of cofactors. Say, how about let me use B to denote the matrix of cofactors. Yeah, cofactor A11, cofactor A12, cofactor A1n. What is cofactor? Formula is here. Yeah, formula is here. Yeah, cofactor. Okay, compute cofactors, then form this matrix. N1, N2, Nn form this matrix. Then A inverse, the formula is 1 over determinant of A. Yeah, matrix A. Compute determinant of matrix A. Then times B, yeah, this B. Cofactor matrix. Take transpose. That is the formula. Yeah. We can use determinant to compute an inverse. This is a section 3.3. Now the next section. Section 5.1. Eigenvalues and eigenvectors. Eigenvalues and eigenvectors. Definition is this, okay? Definition. If this equation holds, here, vector V, non-zero, important. Eigenvector cannot be a zero vector. How about lambda? It is a scalar, but this scalar can be zero, can be non-zero. It doesn't matter. Okay. Whenever this equation holds, we say that lambda is an eigenvalue of the matrix A. Yeah, eigenvalue of matrix A. And the vector V corresponding eigenvector of the eigenvalue lambda. Okay, yeah, this is the definition. Whenever this equation is true, then V eigenvector, lambda eigenvalue. Any example? Let me see. Let me see. No examples that I prepare. Okay, that I prepare. Section 5.2, number 6. Section 5.2. Okay, section 5.2. The characteristic equation. How to find all the eigenvalues of a matrix? Yeah. Okay. Definition. there are two parts. Okay. A minus lambda times I determinant. This is after you expand this determinant, it is a polynomial. This polynomial is called characteristic polynomial. This polynomial, all its zeros are eigenvalues of matrix A. Okay, then how to find all the eigenvalues? Set this polynomial to 0. Yeah, we call this equation characteristic equation. Yeah. Solve this equation for all the roots. Then we get eigenvalues, all the eigenvalues. Let me take problem number 9 in section 5.2. Yeah, to present. Problem 5.2. Yeah. Problem number 9, section 5.2. Okay. Find the characteristic polynomial of this matrix. 1, 0, negative 1. 2, 3, negative 1. 0, 6. Yeah. So solution. Okay. You need to compute a determinant. Okay. Compute A minus lambda I. Okay. Where lambda is a variable. Okay. I is an identity matrix. Okay. This matrix minus lambda I is 1 minus lambda. Then 0, negative 1. 2, 3 minus lambda, negative 1. Yeah. 6. 0 minus lambda. Yeah. Determinant. Now expand this determinant by expansion formula. Don't compute this determinant by reducing it to epsilon form. Okay. Yeah. Because some entries involve the variable lambda. All right. Now I expand. Say for example, I expand this determinant across the first row. The formula is A11 C11 plus A12 C12 plus A13 C13. Yeah. A11 1 minus lambda C11 by formula negative 1 1 plus 1, then determinant capital A A11 plus A12 0. So 0, then plus A13 negative 1. Capital C13 formula negative 1 1 plus 3, and then times determinant of capital A A13. So let me simplify first. Negative 1 to 2 to the second positive 1. And then negative 1 to the fourth positive 1. There is a negative 1 in the front. So minus A13. Now continue here. This is a 1 minus lambda. Capital A11, delete first row, delete first column. Yeah. Minus capital A13, delete first row, delete the third column. Then 2 by 2 determinant, we have a formula to compute a 2x2 determinant. The product of the main diagonal entries minus the product of anti-diagonal entries. Then here, 2x2, so 2 times 6 minus 0 times 3 minus lambda. So this is here, it is 3 minus lambda, negative. Let me put negative here. Then plus 6. Then minus the second term, 12. Done. Okay. You don't need to, simplify your result. You can stop here. Okay, you can stop here. This is I picked this problem to present. Section 5.2. Now the next section. Actually, this is an important section. Section 5.3. Diagonal lines. Matrix, a square matrix. Yeah, square matrix. This is whenever we consider eigenvalues and eigenvectors, the matrix square. Okay, square matrix. Definition is important. So, what is how to diagonalize a matrix? Definition. Okay. Let A be n by n matrix. If you can find a matrix P, this is an invertible, has inverse, and a diagonal matrix D, diagonal matrix D, such that A is P times D times P inverse. Okay, then A is called diagonalizable. Okay. Otherwise, if you cannot find P and D so that this equation is true, A is not diagonalizable. Okay, not diagonalizable. Yeah, this is the definition. Okay. If I move P inverse to the left hand side by multiplying the equation from the right side by matrix P, then I get this. Okay. And then compare the both sides column by column. Then we see the columns of P actually eigenvectors, linearly independent eigenvectors. And the diagonal entry of D are eigenvalues. And why we study this equation? If A can be diagonalizable, then it is easy to solve system of ODE, ordinary differential equations. This equation has applications in the solution of system of ordinary differential equations. Okay, yeah. So very useful. Okay. Actually, this topic is important topic. Because columns of P are eigenvectors, entry entries of D eigenvalues. So how to diagonalize a matrix? 2 steps. Okay. Yeah. To diagonalize a matrix A, 2 steps. Step 1. Find all the eigenvalues of matrix A. Okay. Eigenvalues, we will use them to form the diagonal matrix D. Okay. Then step 2. After we get all the eigenvalues, for each eigenvalue, find linearly independent eigenvectors. Find and linearly independent, because P is an invertible matrix. The columns of P linearly independent. So find n linearly independent eigenvectors. Okay. Of matrix A. We use these n linearly independent eigenvectors to form the matrix P. Take a look at one example. Yeah. Example. This is the example number 3 in the book, page 315. Okay. Diagonalize this matrix. I don't know whether or not I can diagonalize this matrix. If I don't have sufficient linearly independent eigenvectors, then I cannot diagonalize this matrix. Okay. Yeah, we require, because A is 3 by 3, we need 3 linearly independent eigenvectors. All right. Solution. 2 steps. Step 1. Find all eigenvalues. Yeah, this topic important. Okay. Find all eigenvalues. How to find all eigenvalues? Characteristic polynomial. Okay. Compare this polynomial. Okay. Expand it, then we get negative lambda 3 lambda squared plus 4. The root of this polynomial are all the eigenvalues. How to find the roots? Factorization. Don't worry about how to factor a polynomial of degree 3 in the exam. You know, the factorization in the exam should be easy to get. Okay. Yeah, I don't take a matrix too complicated like this. This too complicated. Okay. Yeah, in the exam. Okay. So you don't need to worry about how to factor a polynomial of degree 3. But okay, here now after I factor the polynomial, then I can tell eigenvalues. So eigenvalues. A 3 by 3 matrix should have 3 eigenvalues. First one, number 1, because number 1 make the polynomial 0. Okay. Now the second eigenvalue, negative 2. The third eigenvalue, negative 2, because power is 2. Yeah, so 3 eigenvalues. Negative 2 is an eigenvalue with multiplicity 2. It is a double eigenvalue. Eigenvalue 1 has multiplicity 1. It is a simple eigenvalue. Okay. After I get eigenvalues, then step 2. Find free linearly independent eigenvectors. Okay. Okay. For eigenvalue 1, I first look for eigenvectors associated with eigenvalue 1. How to get eigenvectors associated with eigenvalue 1? Solve this equation. Lambda. Now lambda is 1. Solve this equation. How to solve this equation? Move the right side to the left-hand side. And then factor x out. Don't forget a minus I, okay? Not a minus 1. A 3 by 3, 1 is 1 by 1, not computable. A minus I. A minus 1, this is A, minus identity matrix. Yeah, this matrix. Number three, 0. Solve this linear system, then I get solution is, write the solution in vector because eigenvector is a vector, okay? X3, free variable, times. Then for eigenvalue -2, find eigenvectors. Solve this equation. -2x. Then the solution is, let me see, solution is x2 variable. -1, 1. Yeah. Actually, this vector, eigenvector. Okay. Yeah. This is a eigenvector. Now we have 3 linearly independent eigenvectors. Now, the next step 3. Form matrix P. Okay, yeah. The columns are eigenvectors. We have 3 eigenvectors. Which eigenvector we should place first? It doesn't matter. Okay. Yeah. Okay, I put this eigenvector first. And then this eigenvector second. 1. This eigenvector, the third. Yeah. Form P. Then step 4. Form D. Diagonal matrix. Now this time, the order of the entries depend on the order of the columns of P. Okay. Okay. First column, eigenvector. This eigenvector associated with eigenvalue -2. So put -2 here. Second column, eigenvector associate with eigenvalue 1. So put 1 here. And then third column, eigenvector associate with eigenvalue -2. So put -2 here. If all the computations are correct, then we should have A is equal to P times D times P inverse. Okay. Yeah, you can have a check. Don't check with this equation because you need to compute the inverse. Move P to the right side. Check this equation. Yeah. If all the computations are correct, we should have this equation. Okay, this is the review for the final exam. Okay, final exam. Yeah. Important. Take a review about your homework assignments, and then read examples in the book and try some other problems in the exercise sections. Yeah, let me stop here.